I often see people cite this argument when it comes to AI that they think that 100% they're convinced that there are companies that have some sort of secret tech, or the government has secret tech, that there's secret tech and AI that people have developed, and just no one's released it yet, right? And the bottom line with that is that it's a fundamental misunderstanding of AI as a whole and how AI has progressed. I can break this down to you very simplistically as I can in terms of looking at the history of AI through the scientific advancements of it. This is the best way that I can think of to break this concept down to you as simplistically as I can. And then so we're going to start off with the most historic research paper when it comes to AI. It's the Rosenblatt paper, Rosenblatt 1958, and the perceptron, a probabilistic model for information storage and organization in the brain. And then I can say a few things about this paper. Number one, I can say if this paper came out today, it would be debunked. It would not be published. We would not recognize it up front as valid research. The second thing I can say about this paper is that it's Rosenblatt was philosophically correct and mechanically wrong. That's the best way that I can break this down. So Rosenblatt asked the right philosophical questions, and the philosophical questions are right here. They're the first three in this paper. How is information about the physical world sensed or detected by the biological system? 2, in what form is information stored or remembered? And 3, how does information contained in storage or in memory influence recognition and behavior? He asks the right questions, and then by asking those questions, he envisions the perceptron. And then we see numerous diagrams of this, which is a continually, it's a connected system with numerous connected nodes across a singular layer, right? And then we have more diagrams of it here. Kind of thinking of it like an eyeball, right? Which makes a lot of sense, right? And then so it's an eyeball with connected systems to it, and then gives the mathematics behind it, and then some of the sharp mathematics, more diagrams out the equation for the perceptron as to how it will work, and creates the sigmoid function, which we see here, and then we can see the sigmoid and the S curve within this, and then you create multiple sigmoids and put them together, and then that's what creates the activation function within the perceptron, and then here's a really good, he gets really good into the examples of sigmoid and how this actually works, right? And then so it's and then the equations behind it, and then it's the perceptron itself, and then in this instance it's able to predict binary, right? And then here, and so you get parameters, and this is the first parameterization of a neural network, and he breaks it down, here it is. If you're familiar with perceptrons, neural networks, etc., Rosenblatt 58, right? Here's all of the construction of it here, and submitted and reviewed April 23rd, 1958. And then so a lot of again, philosophically right, mechanically wrong. So what we've definitively proven and advanced since Rosenblatt is the best way to break that down for you, right? So in 1969, the next advancement is a paper called, and it introduces linear separability limits, and is formalized in the Minsky paper. And then so linear separability limits say that Rosenblatt limits can't solve linearly inseparable problems like the XOR problem, and then this limitation was mathematically formalized, and it became a pivotal moment in realizing perceptrons alone aren't sufficient for general intelligence. And then so the impact of this is that it gave birth to the need for multi-layer architectures. This is essentially AI winter #1, right? This paper, where they realized there's extreme mathematical limits to the perceptron as laid out in the Rosenblatt paper in 1958. So we from 1969 on, what they realized, and what you'll see here is a progression of deviation from the original model, right? And then so the 1958 Rosenblatt model was designed to mimic what we knew about the human brain and how the human brain works at that time, and how it worked. But then in 1969, it was proven wrong. Like, you're wrong, sir. It doesn't actually work this way. And then it has limits. And then like that caused like this, so like 1969 to 1986, that's the AI winter, right? And that's the period of the AI winter. And then so in 1986, there's this introduction of backpropagation and multi-layer networks. And then backpropagation is primarily attributed to Jeffrey Hinton. And then so they made backpropagation and multi-layer perceptrons, and then they trained them on lots of data, right? And then so that's the two major breakthrough. That's what they won the Nobel Prize for. And then so this shattered the limitations of single-layer perceptrons and allowed for non-linear decision boundaries and deep representation learning. So this, like the Minsky, so you have the Rosenblatt paper in 1958. The Minsky paper comes out in 1969 and says, "Hey, bro, you're wrong, dude. Like, this isn't going to work. None of this is going to work. It kills all of AI research." You get the first AI winter. And then 1986, Hinton et al. Introduce backpropagation and the multi-layer perceptron, which overcomes the Minsky limitations and then puts it back on track, right? And then so we start moving forward from there. But the important thing to realize and to understand, and this is very big, especially for Jan LeCun, right, which is that this creates a major fracture away. Like, so this introduction is very significantly different than the original perceptron architecture. Significantly different. And the original perceptron architecture was meant to be a model of the brain. It ended up being a wrong model of the brain, but that was the original intent, was for it to be a model of the brain. So then you might start introducing and asking yourself this question as to why exactly is this working here, which would be a good question, right? But so before we get to that question, we get 3 years later another introduction, which is the universal approximation theorem in 1989. So a multi-layer perceptron with at least one hidden layer and sufficient neurons can approximate any continuous function on compact subsets. So this is this mathematically closed the debate. Neural networks, in theory, can model arbitrarily complex phenomena. This was like, it's like, here's a mathematical theorem that says like P equals NP, right? Basically that, like, and the model can solve for P equals NP if you give it enough parameters and enough compute behind it. And then so people think this, but then you notice the biggest breakthrough doesn't come again until 2006, right? Because AI Winter 2 Electric Boogaloo kicks in, and then what happens is essentially you have so these two advancements are very significantly different from this, right? Like, I'm sorry, and from this, which is like again, modeled off of the human brain. And then so we introduce these two things right here, which are like significantly deviating from it. And it's like taking it into like an alien brain essentially. And then people are like, oh, that's not like how it was, and it shouldn't work that way. And then so you notice 1989 to 2006, because that's people are like, AI is garbage again, right? And then so 2006 to 2012, that's where you have the introduction of deep learning and representation hierarchies, which deep learning is like, okay, let's like actually create like multiple like matrices and attach them together, and you get autoencoders and restricted Boltzmann machines, deep belief nets, and so again, Jeffrey Hinton coming in, and then later convolutional neural networks, which are like and transformer-based models, and then you get advanced Rosenblatt ideas into. So they take Rosenblatt's initial ideas and then they introduce like multi-level abstractions and hierarchies, which his perceptrons could never, ever, ever scale into, right? And then so at this point, we have gone completely away 1,000,000% from the original intent of perceptrons, which was to be a mimicking of the human brain. And then all of this is like, well, if we scale perceptrons, and then we do stuff to it, it ends up working. And then so we're just going to roll with this, and then all of the initial stuff like the Rosenblatt 1958, all of that tied to the human brain, we're just going to like kick that out. Right. And then that's where you then have the big introduction of what people talk about like all of the time with LLM models, which is gradient descent optimization. Right. And then so that kicks in, and then you get like the atom optimizer, and then loss landscapes, and then curvature aware optimizers, and then all of this is like a major advancements, but it's a significant gap and like something that Rosenblatt never had within his theories, right? Like within Rosenblatt's probabilistic formulation, all of his equations, not a single part of this was factored into it, right? Or measured into it whatsoever. So this is again like another deviation. So we have perceptrons, which are end up being like a failed architecture in and of themselves. They don't work, but then we modify that architecture, and then a very few select group of people modify it, and then that ends up taking off and having benefit, and then they modify it more by building out deep layers and then gradient descent, and then we get into like Bayesian neural networks and variational inference, and then you get into like the introduction of like Monte Carlo algorithms, and then those get invented, right? And then so you get more complex math that gets thrown into it, and then so like you get like probabilistic reasoning moves away from just that simple S curve, and then you get like Bayesian deep learning, Gaussian processes, uncertainty quantification, chaos theory as a mathematical concept takes huge leaps from like 2005 to 2015, and then you get from there, expressive power and capacity theory, which is essentially like scaling theory, right? Scaling law. And then so we've scaled that out, and we've done with that, and we can prove that out in lots of different things. And actually, Rosenblatt did touch on this vaguely, right? But modern theory, so like and that's where like Rosenblatt was like bringing it and tying it back, like philosophically right with a lot of these things, just mechanically wrong. And then in 2017, that's where you have the introduction of the transformer architecture, which is like a completely non-perceptron-based departure, right? Like we've essentially abandoned perceptrons as the base at this point. Transformers become the new base, right? And then they're all wrapped around attention. Attention mechanisms enable global information flow without spatial constraints. So they take like the sigmoid function. They take a lot of perceptrons, and then they just bundle it around attention. And then transformers prove that local connectionism is not a hard requirement for learning. That's the big significant thing, right? They prove that you can just have like probabilistic functions within that. Next big thing is unsupervised and self-supervised learning, which are two concepts that Rosenblatt never he didn't think that they would work. It's only supervised learning, right? You need data, and supervised learning is the only way, and that's everything that is in Rosenblatt 58. And then as we can see now, self-supervised learning and reinforcement learning, as we've seen recently, actually beats supervised learning even for LLM models. And then so even for the models that Rosenblatt thought supervised learning would be the only way, reinforcement learning and self-supervised learning are actually, and unsupervised learning are better methods overall. And then also we get into scalability and emergent behavior. Rosenblatt never imagined that you could scale a model because of the Minsky paper mentioned up front, right? They ran into that. So Rosenblatt in his lifetime never knew that you could overcome those scaling limitations. And then so now we've proven that you can, and then we've also proven scaling laws within that. And then also, since then and since that time, we've also had the introduction of geometric and topological deep learning. And then so we've made significant grounds both within the mathematical theory and the physics-based theory with regards towards these two areas, specifically within the last 10, 15 years. And then we've also had significant advancements within neuroscience, right? So neuroscience-inspired architectures that have been revisited and imagined. And then you have I mean, today I've seen like there's actually like a literal commercial brain that is some companies marketing it, right? Like it runs on literal like human I don't know, not human brain, but like brain matter that is it's an actual biological computer, right? Biologically fidelity, and so all of that and none of that was envisioned during Rosenblatt's lifetime. So what the major point of this is what has not been definitively proven and is just empirically successful. Like this is the most important part, right? So this is the history. If you don't take away anything else, remember these things. So we still overall there's still questions and it hasn't been formalized why deep networks generalize so well despite their overparameterization. Why do deep networks generalize beyond a data set at all? We don't have a formalized answer for that, and there's not a theory behind it that's a formalized, this is the scientific theory. Second is true biological equivalence between learning mechanisms in the brain and ANNs. So there's I mentioned that at the beginning, Rosenblatt introduces his theory based off of the brain, which ends up being wrong, and then we end up deviating significantly from that wrong theory. And then so we've never, ever been able to unify the two. We now have what we'll call an alien brain architecture versus what we initially were going for, which is the human brain architecture, but the alien brain architecture is doing stuff that we didn't envision, but we haven't been able to join and say why it works. And then the third thing is a full theoretical understanding of emergent abstraction and unsupervised models. There's not a universal and really any dominant theories with regards towards emergence and why and how and what are the exact parameters, etc., that it occurs within models. It's just been documented that emergence occurs, but we don't know what the mechanisms are behind that formally in any formalized research. And then the fourth is whether symbolic reasoning can emerge naturally from continuous gradient-based architectures. And then this is a big question, right? And this is the thing that people criticize overall about the models overall. So that introduction of that loss function, that the NM optimizers here, right? This right here is people debate this up and down. So the two biggest things, there's a huge amount of debate around this, and then there's even more, I'd say even more debate around this. These are the two big, everything else is secondary compared to these two, number 2 and number 5, and then within that introduces the question, are they actually learning, or is it actually just work? Is all of this working just because of number 5? If we take out number 5, it all doesn't work, right? And then so it wasn't working. All of this was pretty garbage until number 5, right? And then and you look at it, so it's from 1958 until the introduction and the post 2012 of number 5, and that's what rocket fuels all of this, right? And then so this is pretty recent, and it's just one thing, and it's a major deviation from all of this before it, right? And then so that there's a big question mark there. So Rosenblatt gave us the seed, learning via wiring updates, statistical separability, and distributed memory. And then, so what we've proven since is how to scale, how to stabilize, generalize, and compose those principles into deeply expressive systems. But ironically, some of his limits, inability to abstract relationships and need for better dynamics, are still echoing in today's frontiers. So the bottom line and the next step to take this is what we knew about intelligence and cognition in 1958 versus what we know now about intelligence and cognition within 1958. And then so if you blended this, right, the history of where AI is and has been, and then you meld it and you put it on top of this, it gives you a 100% crystal clear picture from both sides, from both the technical side, this is the computer science side, right? And then you have that second side that I left out, which is like we now know more about the brain, more or less, about how the brain works as a cognition model overall, right? And we have new theories that we definitely did not have in 1958. And then so we have new theories in 2025 that didn't exist in 1958, which have led to new and different architectures that do exist overall, but they're all like none of these architectures have been proven out in any of the same way that Transformers has. Right? You hear about Transformers and there's all of the money behind Transformers models because that's just been what AI research has been built off of. But like Transformers models are all built off of this, right? Like this is the path of Transformers models, which is the Rosenblatt path, right? The 1958 path, and then deviations from the 1958 path. But none of those deviations from the 1958 path have crossed into this. So you have like two aspects of AI research right now, right? You have this path and this path, and then it's like if you like I think that this path is the answer. A lot of people think that this path is the answer, but this path is the path that you're dumping all of the money into. So like there's no other simpler way to break that down, right? Like hopefully that this is like the aha moment for you, right? Like why do people like why are the like people that are so advanced and far into this think these things? This, right? It's because there's a distinct schism. Like what you want is based off of this. Hopefully I've given you what it like and shown you and showcased to you what that is, right? And it works. It does work, but it's the big question, right? Like and people knock it up and down, right? Like it's like on both sides of the argument. Like people that are like very for and pro AI overall will still say that it's not like AI in its current form is not actual reasoning because of this, even though they're like pro and for AI, because it like this is so gradient descent is and gradient descent optimization is very straightforward as a concept. And explaining it into simplistic terms, I've explained it before, right? But so you have like a topological structure within a data set. And then so within that topological data set and topological structure, we're thinking of it like a 4D plus structure, right? Which is hard for the brain to wrap your head around. But so it has peaks and valleys within it. And then there's, let's say, like lots of peaks and valleys, right? And like it's mountainous, and then some are valleys, and then some valleys are lower than others. Like some valleys go below sea level. And we want the lowest valley that exists. And then the gradient descent says find whatever the lowest valley that exists is, and then go in the complete opposite direction. And then, but sometimes we'll find a valley, but it won't be the lowest valley that exists. It's just a good valley. And then so it'll get us like 80% accuracy. But if we had found that valley that was the deepest, we get like 98% accuracy. But so that's where gradient descent adjustment comes in. And that's all you're doing, right? Is you're basing it off of natural gradients within the data set itself here, right? That's why it's called gradient descent. And then so within that is that actually learning, and then that's very 100% different than what Rosenblatt laid out in 1958, and then that's very 100% different than everything that we know with regards towards modern cognitive architecture. So then bringing this forward, right, and then so this question here, or the statement here at the top, that there's no hidden secret bunker AI tech. Like, so the bottom line is that like this is technology that was first introduced in 1958. It was then you have a major schism in that camp. Like people don't agree on within it as to what the way forward is, and then no one understands why exactly it works, because the original like reasons and architecture for what it was built on is flawed, mechanically incorrect. So all of that combined leads us to where we are today, which is a lot of questions, right? I mean, really, we are in like this is like Betamax versus VHS, right? Which one is going to win? Like, and we've been in this situation a lot where like, and people like to put themselves in this binary situation for some reason, where you have two competing architectures, right? So this is the one that everyone's backing right now, which is Transformers, and then you have we'll call it like a Blu-ray versus like your Blu-ray versus HD DVD, right? And I would say this is HD DVD, this is Blu-ray. Which one is going to win out in the end? I'll put my money on Blu-ray. But so if you like, hopefully this gives you a fuller introduction, right, as to why like no one has secret tech into this, because if they did, they have secret science that no one knows about. Like they've solved quantum mechanics to levels that are either surpassing this or surpassing this, and then they're two vastly different tracks, and we don't understand overall how either one of these work in the long run. So at the point where no one can prove that out or has solid answers as to how it works at the top, there's nothing hidden within it, right? Every single advancement is getting us closer to understanding how it works. And then so there's nothing to hold back, right? Like we're all in the same boat of trying to understand how it works and what's going on within it. What are the levers? Like we're all just trying to find levers, and then some are betting on this lever, some are betting on this lever, and then that's what the ultimate race is. And that's all it comes down to. It's not any like more rocket science than that. And so if you like this type of content, please like and subscribe. Thank you very much.